Good afternoon, everyone, and welcome to the latest SCLF webinar. For anyone who doesn't know me, my name is Alison. I'm the current chair of SCLF, and I will be your host today. And I'm joined by Stephen Collins, another member of our exec team backstage, who will help with any technical issues you might have during the webinar. If you have any, then just stick them in the questions box. Before we get started and introduce Ian, we have just an announcement and some housekeeping. So you might have seen that the SCLF conference is back in person this year. Unfortunately, Ian was going to be speaking at the conference and then we changed the date so he couldn't do it. So we've set this up for him instead, which is absolutely brilliant that he was able to come along today. So you can join us on the 25th of August in Glasgow, and we'll also be live streaming as well, hopefully. And you can find out more on our conference webpage, and I'll stick all the information on that in the chat in a minute or two. We also still have some exhibitor spaces, so you can sign up for that as well. So in terms of housekeeping, you'll have joined today on mute, and your camera is off, so you can just sit back and enjoy today's webinar. And if you do need to step away, then don't worry, we are recording the session and you'll be able to catch up again on our YouTube channel later. And again, I'll put the link for that in the chat. If you do have any comments or suggestions or questions for Ian, then please stick them in the questions box. And we will try and get to them at the end of the presentation. And if we don't, then we will try our very best to answer them offline. And last for the housekeeping, when you exit the webinar today, you will be asked to fill in very, very short feedback form. We'd be really grateful if you could fill that in. And in that form, you can also provide any suggestions for future webinars or speakers. So without further ado, we'll get on to today's session, and I'm delighted to welcome Dr. Ian Bishop to present today on what appears to be quite a perpetual hot topic of TPH, and is it always TPH? Something that we spoke about in SCLF 25 years ago. Ian is the founding and managing partner of One Touch Data, who produce and support the industry standard hazardous waste classification software HAZWaste Online. His background includes geology, geophysics and environmental data management, and 16 years working for Golder Associates. He started One Touch Data in 2008, just as the banking system crashed, and the crisis leading to a change in the direction of the development of HAZWaste Online, which has become the go-to software for waste classifiers in the UK and Ireland. And today he spends a lot of time working with stakeholders to help improve standards and understanding across the industry, and that's exactly what Ian is going to be doing with us today. So without further ado, I'll hand you over to Ian. Thanks.
Thank you very much, and thank you everybody for joining us. I'm going to talk a little bit today about TPH, and is it always TPH, as you can guess from the strapline. So if I can advance this. And I'm going to talk about what the lab actually measures and how to use the TPH data and make sure you're getting the data that you think you're getting. So what do you actually understand about your TPH results? So these are some of the topics I'm going to touch on today. What's the difference between the different types of lab TPH test? You've heard of things like EPH, TPH, TPH1, Texas method. What are they all about, and how does one lab compare to another lab? Another key thing I'm going to bring up for those of you who do human health risk assessment type work and you ask for TPH CWG, that is no longer the same across all the labs. There's a technology improvement that about half the labs have moved on to that you might not be aware of. You might have asked this question: why is my the mineral oil result in my WAC a few times bigger than my TPH result, and therefore I might have a non-hazardous soil, but for some reason I'm failing the WAC waste acceptance criteria? I've already touched on this one. How can I compare results from one lab to another? Most of us get data not from our favorite lab, but we might be getting it third hand from another lab. It's being passed on and we have to process it. And one of the challenges then is trying to work out what that lab has done and why it might be different from the lab you normally use, even for the same materials. The new test I've been alluding to is called GCGC, or 2D gas chromatography, I'll be explaining what that is, where that is having a significant impact on what we're doing, both in waste classification, in WAC analysis, in your human health risk assessment type work. Another thing that you need to be cognizant of is where labs do interpretations. Okay, it depends what they tested as to effectively what type of interpretation you might get. I'll give you some examples later. And the key question I want you guys to think about is the TPH that you get from your lab, whichever method the lab used, is it actually from petroleum hydrocarbons, or could it be from another source? So other sources might be from coal tars, it might be from ash, etc., etc. I'll pose one question to you. If you think about the major fuel through the 1800s, 1900s, in our houses and our factories, I think most of you will come up with coal. If I then say, well, where did the ashes from the fire grate go? Many of you would think, well, thrown in the garden or trapped over the wall. So when you're doing your site investigations and you're digging your holes and taking samples, another reason why you might not be actually detecting petroleum hydrocarbons, they're hydrocarbons produced from the refining of crude oil, instead hydrocarbons from other sources. So to start answering these questions, we really need to understand how hydrocarbons are measured by the labs, consider other sources of hydrocarbons, and of course integrate it with the other information we got about the site. Now, while I'm talking mainly about soils today, this will also have applications for any of you dealing with other materials, other waste streams, for example, whether it's filter kegs, sludges, dredging waste, doesn't really matter. You still need to understand your TPH. So the real challenge is there's no consistent system for the terminology across the labs, and it can vary from lab to lab. So just to give you some basic definitions first, again, give you a handle on the acronyms. So TPH, total petroleum hydrocarbons, comprises hydrocarbons within the range in our world of about 5 carbons all the way up to about 44, and includes a group called the aliphatics, which are the simple carbon hydrogen molecules that you find in fuels, and also the aromatics, which are these ring-based molecules. You can see benzene over here on the right. Another term you hear from your lab, or some labs, is EPH. Now, the acronym is extractable petroleum hydrocarbons. And these are the hydrocarbons that you extract from your soil, your filter cake, your sludge, using a solvent. And generally, labs report this in the range from about C10 all the way up to about C40. So that is everything extracted from your material. Then you can have what's called a cleanup step. And this is where you take that original extract and you run it through a cleanup system. And you may have heard of silica gel and Fluorosil cleanups. And the idea of the cleanup is to remove non-petroleum hydrocarbons. So if you're thinking of a soil, for example, the non-petroleum hydrocarbons in the soil are things like your humics. Humics are the breakdown products from bacteria and dead leaves and everything else. We're all made of hydrocarbons at the end of the day, but they are non-petroleum hydrocarbons. And the key difference between the petroleum hydrocarbons, like these you see towards the top of the page, is they contain other elements such as oxygen, nitrogen, stuff like that. So humics and fatty acids, you'll find these in soils. None of them are petroleum hydrocarbons. And if you don't do that cleanup step, so you just analyze everything extracted from your soil, you will get an inflated number depending on how many humics type molecules you have in your soil. Diesel range organics, DRO, is another term that you see the labs produce. It stands for diesel range organics and generally covers the range from about 10 carbons to 25. Key thing to appreciate there, that does not mean that you've got diesel. Okay, there are many other fuels that fall in that range. Kerosene falls in that range. Light fuel oils fall in that range. It's just a descriptor to focus on the range of 10 to 25 carbons. Another common misused term is mineral oil. Also generally from about C10 to C40. strictly, it should be the same as the cleaned up EPH. So it's gone through a cleanup system to remove those non-petroleum hydrocarbons. Now, mineral oil, you'll all be familiar with, if you're purchasing WAC data from your laboratory, there's a line item there called mineral oil. Another term you'll hear is the gasoline range organics. So this covers the more volatile organic compounds, petroleum compounds between C5 and C10. You'd also hear terms like headspace analysis, and this is just where you put your sample in a little brown jam jar, keep it cool, send it to the lab, and they effectively analyze the gases, the volatiles above your soils. This is also the same analysis that gives you results for the BTECs, benzene, toluene, ethyl benzene, and xylenes. And then we have many of you, your favorite, your TPH CWG from the criteria working group. This was a document written in the late 90s, which was focusing on this problem of petroleum hydrocarbons versus other hydrocarbons. And so they came up with this kind of approved method, I guess, for extracting and then cleaning up the soils to just focus on petroleum hydrocarbons, and in particular, clean up to look at the aliphatic fraction and the aromatic fraction. So in fact, they actually do two cleanups rather than just a single cleanup. I'll explain more about that later. And then once they've done the cleanup into the two fractions, the aliphatics, which are the simpler hydrocarbons, and the aromatics, your benzenes and your PAHs and stuff like that, they then put them into bands, and that's what some of you will be using in your human health risk assessment. Now, for those of you who are also doing waste classification, just be aware, one little bit of advice: if you're purchasing or using TPH CWG, typically that only goes up to C35. Okay, and that's what you need for your human health risk assessment work. For waste classification, we need to go up to 40. Okay, so if you have your standard test suites with your companies and on there is TPH CWG, just make sure that you tweak it so it goes up to C40 or more. Okay, because C35 is not enough for waste classification. So, importance of the cleanup step. Oils are derived from the refining of crude oils and comprise primarily molecules with carbon and hydrogen atoms. In waste classification, we have to look at petroleum hydrocarbons, from oil spills and unknown oils. So what I'm pointing at here is we're talking about oils produced from the refining of crude oils. But soils can also contain other hydrocarbons, fatty acids and humic acids I've mentioned. Here's a fatty acid here, and you can see the oxygen and the hydroxide ion on the end of it, group on the end of it. And over here, this is a humic acid, and you can see oxygen, you can see nitrogen and things like that. So these guys are different from the hydrocarbons from refined oils. And the idea of a cleanup step, it's not perfect, is to remove these non-petroleum hydrocarbons from your total extracted hydrocarbons, from your total TPH, and give you, it'll tend to give you then a smaller number. So let's just understand a little bit about how the laboratories do the basic testing. So the preparation method for whether you're doing EPH, which is everything extracted in the language I'm using today, or TPH CWG, is you take a solvent, might be hexane, acetone, dichloromethane. These are all solvents, and different labs use different ones. And you mix it with your soil, you shake it all around in a machine for half an hour or however long they do it. And the idea is the solvent then extracts all the hydrocarbons from that soil, and you end up with a milky colored solution, which is what you then use to put into your gas chromatographs. So for EPH, you take the extract and you run it into a gas chromatograph, that's the GC. The FID bit is the detector, it stands for flame ionization detector, and this is what produces a chromatogram, a series of little spikes with time on the x-axis down here. So this EPH effectively measures all the hydrocarbons extracted from your soil. So that would include your humics and fatty acids plus any petroleum-based hydrocarbons. TPH-CWG takes the same extract, but there's effectively 2 cleanup steps. Typically, the labs that still do it this way use a silica alumina cleanup column, and they run it twice. So the first time they run your extract through the column using hexane as a solvent, and this they use the word elutes. This elutes the aliphatics, okay, and leaves the aromatics stuck inside the column. You then take that column and run it again, but this time with a slightly polarized solvent, dichloromethane, and that will pull out the aromatics. Now, none of this chemical treatment is perfect, and there are always problems and limitations, but that's effectively what happens. Now, so you've got 2 outputs from TPH-CWG, and then you run both those outputs, both those elutes, into a gas chromatograph. So you will get 2 chromatographs if you ask for them. So there's an example. This is the aliphatics. C20 is about here, and this is aromatics. I'll explain chromatographs a bit more in a minute. So how do you know what your lab has actually done is the key question for the first part of this talk, because the terminology they use varies from lab to lab. From the name alone, you can't really determine what they've done. And for those labs that do put some brief method statements in the back, they're often clear, and quite often they don't even mention a cleanup step, whether one was done or not. I've also found that the term, whichever TPH term they use, it can vary between the quote, the schedule you might receive from the lab, and the PDF report. Now, for most of you, if you only ask for one TPH test, you don't notice this because you get a TPH result and it doesn't matter what it's called almost. But I do a lot of forensic type work where I ask for everything extracted, I ask for cleaned up and other bits and pieces, and knowing which one you're dealing with is far more important. I've even found cases where they've used the same name for the TPH in both the solid part of the report, where your total metals are, for example, and also in the WAC report. So I've had mineral oil with 2 completely different numbers in the 2 reports because they've used completely different approaches. One was cleaned up and one wasn't. So here's some examples of a selection of terms. I defy anybody from looking at those to tell me which ones are cleaned up and which ones are not. We'll come back to that list in a minute. So what we have done to try and help solve this problem and create a standard effectively across the UK and Ireland, and we've even got some European labs coming on board now, is to introduce the HWOL Acronym System. Okay, it's a series of 2-letter acronyms that you string together, or the lab strings together, and puts against their TPH results. So every determinant that's related to TPH, every band, every fraction, for example, will have a series of these acronyms. So this is the headline list. So HS for analysis of the headspace, MS for mass spectrometry, I haven't mentioned that yet. EH is for all the hydrocarbons extracted by a solvent. CU is the critical bit, means there's been a chemical cleanup, either a fluorosil or a silica gel, the 2 that you come across. And then we have 1D for single coil gas chromatography. Total means we're getting the sum of all the aliphatics and the aromatic fractions that have been measured, whereas AL is just the aliphatic fraction, AR is the aromatic. And then we've got the new technology, GC-GC is the common name for it, 2D GC-FID is another name for it, which is double coil. So instead of using a single coil, they use 2 coils in the chromatography. And then, as opposed to this chemical cleanup route, there's some of the labs to deal with the cleanup for 2D gas chromatography, they use a mathematical cleanup approach. And once again, I'm going to explain these in more proper detail in a minute. And then there's another symbol you see, the plus, which is just for joining tests together. So here's that list I showed you earlier. Okay, and none of you, I'm sure, can tell me which of those are being cleaned up. You may recognize some from your lab. Perhaps your lab uses TPH1, for example. But if I add in the acronyms, okay, and let's just focus on the mineral oil ones at the bottom to kind of help you get your head around what we're trying to do. So we've got 2 mineral oils here. Both of them might be found on your WAC report, for example, from 2 different labs. This first one here is everything extracted into a 1D gas chromatograph, and it's the total of all the aliphatics and aromatics. So that's everything extracted from your soil. That's going to give you a big number, or bigger number. Whereas this one here, which first pass looks exactly the same, has this extra CU step in it, the cleanup step, and it's effectively just giving you the aliphatics. That is what I define as mineral oil. And also for those of you, if you want to discuss it further, if you look in the waste legislation, or rather the landfill legislation, the decision that defines all the waste acceptance criteria, it has an EN standard in there that is prescribing that, a cleanup step. So that's in the legislation. Now, often labs won't be aware of that unless it's pointed out to them, but the mineral oil in WAC should be cleaned up to remove humics and fatty acids and all those non-petroleum hydrocarbons. And that's going to give you a smaller number, which means if you've got a non-hazardous soil and you're trying to get into the inert category of landfill, you're more likely to get below the 500 milligram threshold because you've gone through a cleanup step. So here's an example. Hopefully you can see it on your screens. This is from a lab, and this is probably 3 years ago now. I know the lab has changed their practice since, but when we bring the labs on board with our HWOL data file, it's a file for transmitting data from the lab straight into HazWaste Online. We go through an accreditation process, and that's been expanded to include the HWOL acronyms. And all the UK labs are participating in this and should be putting these acronyms on their reports. So what we have here is we've got EPH 10 to 40 with the acronyms. So this first one is everything extracted. There's no cleanup step. I've also asked for another test, which is a cleaned up EPH, and you can see the CU in here. And you can see the numbers are smaller. Okay, 2,700 for everything, 1,500 for after a cleanup step. This next 2 blocks are our TPH CWG. And you can see this particular lab uses a mass spectrometer to do the C5 to C10 components. And down here we have the sum of all these individual fractions. So you can see here, this is everything extracted with a cleanup, plus the headspace analysis, 1D gas chromatography, and the total of all the aliphatics and aromatics. And this tends to give you a smaller number. Obviously, every soil is different because there's losses when you do 2 cleanups. This is the mineral oil in WAC, and the lab has now changed its practice, but at the time, they weren't doing a cleanup. So you can see they got a much bigger number. Okay, so if anything you take away today, you want to make sure that if you're relying on waste acceptance criteria data, that you want to make sure that your lab is doing a cleanup. So you want to see a CU in this acronym effectively. So what is gas chromatography? How does it work? Well, this is a, you can call it an oil spectrum plot. I call these chromatograms. And what we have on here, we have time in minutes along the bottom. Many labs, or most labs, call it retention time. And then we have a series of spikes representing, at a simple sense, different molecules. And you have the smaller molecules. So you've got C6, C9, C14, C33, 35, and you can see a bit more further down. So these are the different molecules, a simpler sense, coming out of the chromatograph. And they give you this spectrum, or this like fingerprint for the oil. So how does it work? Well, if I take you all back to school, and in school I did it with chlorophyll and leaves, and that was a fairly long time ago now. Some of you may have done it with an ink pen, and you'd have taken a bit of filter paper, you'd have drawn a little blob on one end of it, you'd have dropped the filter paper or dipped it into a solvent, some alcohol, and you'd have watched the solvent front move up the piece of filter paper, and you'd have seen your single blob separate into 2 or more blobs and move up the paper. So if you take that piece of paper and put it on its side, all right, so and then we include time. So we've got time 0, let's say that's when we dip it in the solvent. And then we've got a detector at the other end, which just measures when a blob goes past it and how big the blob is. And that effectively, each blob going past is a peak in a chromatogram. Now, obviously, gas chromatography is a little bit more complicated than that, a bit more sophisticated. These are some of the acronyms that you will see on your lab reports: GCFID, GCMS, GCGC. So I'm going to explain how these work, but if we take GCFID, or 1D gas chromatography is another term that you'll see used. You've got 1D gas chromatography, which is a single coil analysis, and then you've got the detector, which is, in this case, is an FID, a flame ionization detector. Alternatively, you can use a mass spectrometer, and you can look at your individual peaks. GCGC is a new kid on the block. It's been coming through over the last 2 or 3 years, and at least half the labs have moved across to it because it's meant to be more efficient and easier to use. 2D gas chromatography, and once again, you can either pass the output into a flame ionization detector or into a mass spectrometer. Now, most of the labs who have these systems are just using the flame ionization detector output to give you your results. So this is 1D gas chromatography. And if you go to the lab, you'll see a little plastic box like this with a door. If you open the door, inside it looks like your oven at home with the fan at the back and heating elements. But you can also see this coil coming in here, which is laid out in the 3rd picture at the bottom. So what happens is you have your oven with your coil inside it, your column. You inject a carrier gas. You take your TPH, your extract, you warm it up to volatilize the molecules, and effectively the oven also ramps up in temperature, and effectively the smaller molecules go around first and come out to the detector, followed by bigger and bigger molecules. Now, then you get to the detector, and you're either pushing it into a flame ionization detector and getting one of these little spiky plots, or you're using a mass spectrometer. And once again, I'll show you that in a minute. So this is the flame ionization detector. Here's the output from the column. Effectively, they have a flame with a basic voltmeter around it. And when each group of hydrocarbons comes through, each blob, each peak comes through, the hydrocarbons burn and introduces ions into the flame, which is then picked up by the voltmeter, and that gives you one of these peaks. So here's an example for diesel. Okay, so here we have retention time at the bottom. This first big peak that you sometimes see on plots is the solvent going through, so you can ignore that one. And then you can just make out C10, 11, 14, 15, here's 17, 18, and we're up to what, 21, 22, 3, 4, 5, even 20, C26. So it looks a bit like a hedgehog or something. Now, one of the things that you have to do if you are classifying according to WM3 is if you have an unknown oil, there's a particular marker that you can use to discount certain hazard properties, carcinogenic and mutagenic ones. Now, one of the questions you have to ask of your lab is, does my unknown oil contain any diesel or petrol? All right, now, and it's a simple yes or no answer. It's not the same thing as an interpretation. Now, the way that the laboratories can quite easily determine whether you got diesel or whether it's diesel or not, even when it's weathered or degraded or mixed with something else, is they look for these 2 double peaks. So you can just see the C17 peak is slightly thicker on this picture, and then you can see the C18 one. You can actually see the second peak. They're looking at these markers called pristane and phytane. which if you blow the peaks up, which is what the labs can do, you can see them more clearly. And this is distinctive for a diesel, and that's how they can usually quite easily determine whether or not there's a diesel in the mix. So moving on to GCGC, or 2D gas chromatography. They're all names that you might hear depending on which lab you use. If I just remind you about single coil gas chromatography, where you have a single coil inside a little oven, goes out to the detector and it burns it effectively, and you get a peak for every little blob passing through, every hydrocarbon passing through. Now, the limitation of 1D gas chromatography is that one of these peaks could actually be more than one molecule. They call it coelute. They could come out of the detector, after the oven at the same time, and two or more molecules could contribute to one of these peaks. So this is one of the advantages of GCGC, in that it separates those peaks. So the way it works is, instead of having one coil, it has two. You have let's call it a non-polar column, a normal coil, and then you have another coil they call it slightly polar. Let me explain this a bit more. Inside your oven or ovens, you inject in your material into the gas. It goes around the first coil. Smaller molecules going around quicker than the bigger molecules. And when they come out, instead of going into a detector like they do in the 1D system, it goes to something called a modulator. Think of the modulator as a doorway that just opens and closes every couple of minutes. So when it opens, it lets out let's say one of those peaks, one of those bunches of hydrocarbons. It lets it into the second coil. And because the second coil is slightly polarized, it will separate out the molecules so you can differentiate them. So what does it look like? Well, this is a pretty picture I just grabbed off the web, but effectively there's two dimensions to it. This is kind of the normal. If you imagine this thing, this is looking along this edge, and then we've got the second direction. So let me try and explain. When it comes out of the second coil, it goes into the flame ionization detector, and you get a spectrum, and that's plotted in this up-down direction. And then the doorway opens again, and you get another one coming through, and that's plotted in the next slice, and so on as you go across the plot. So these are lots and lots of slices all stacked up together. And you can then obviously contour it with these pretty colors to make it look more interesting. But how do we actually analyze it? How do we actually look at it, I should say? Well, this is our diesel, a conventional single coil gas chromatography. Okay, and if we look at the same thing then on the GCGC system, this is the pretty 3D promotional plot. So here we have our kind of normal retention time, and then this is the other direction. So you can see these are all elongated and up and down the page. So these are each of the slices, each of the blobs that go through the modulator plotted in this direction. So what you have on here, this big set of peaks at the front are your aliphatics. Okay, effectively what you're seeing in the normal chromatograph, and you can see them projected onto the back. So that there has some similarity to this. So these are what they call the saturated hydrocarbons. This is where your diesels and your kerosenes fit. These are all carbon atoms, either attached to another carbon or to 3 other hydrogens, or up to 4 other atoms anyway, of either carbon and hydrogen. And then behind you can see these little smaller peaks. These are some of your aromatics. Okay, so this is where benzene would pop up, for example. Let's look at it in a bit more detail. This is from an oil spill, which once again I got out of a paper. You can see reference there. So this is looking at it in plan views. It's looking down on it. So rather than, oops, go back a bit, rather than looking at it from like a mountain picture, we're looking down on it like a map. And what you have here, you have the colors. So obviously blue is nothing, and then you've got whites going to red and then darker reds. Those, all the little bright reds are the peaks. So in this band at the bottom, between these two lines, this is one term it's used is saturated hydrocarbons. Every carbon is attached to 4 other atoms. So this is where your kerosenes and your diesels would tend to fit, and your lubricating oils. Then in this section here, we have the benzenes and the alkyl benzenes. Your alkyl benzenes are your toluenes, your xylenes, and other molecules. Effectively, you've got methyl groups, one or more, attached to a benzene ring. Then we go into our naphthalenes. That's 2 benzene rings, fluorines, phenanthrenes, pyrenes, chrycenes, and so on. These are your PAHs. Now, you may think, hold on a minute. I asked for a PAH suite from my laboratory, and I get 16 of them, which is fine. You do. That's the standard approach. Just want to make you aware there are many other PAHs, polyaromatic hydrocarbons. So you can have fluorines with methyl groups attached to them, for example. So we only measure a tiny subset of the total ones that might be there. Now, in an oil, you'll also get over here on the right things called hopanes and stearanes. Now, we don't get these in our refined fuels. They're processed out or converted, so we don't see those in our contaminated soil so much. So, how does the lab then give you your concentrations that you have for your TPH CWG? Well, here's a pretty 3D picture of a mixture of aliphatics. This is probably a diesel. Some aromatics, and here's your benzenes and the smaller PAHs like naphthalene. And then over here is this hump, which is generally described as lubricating oil when the lab assumes you're dealing just with oils. So if you look at it in plan view, looking down on it, what the lab does to calculate the concentrations for you is they add in a calculation grid or a stencil positioning standards. They've all got slightly different names, but effectively it's this grid that you can see. So along the bottom here, we've got, you can just make out the aliphatics. So this is C8 to C10, C16 to 21, 21 to 35. This big blob here is this lubricating oil peak. And then we go up to C40. And then above in these larger polygons, we've got the aromatics, 8 to 10, 18 to 21, 21 to 35, etc. And effectively, all they're doing is a mathematical integration to calculate the contribution from all these peaks within a given fraction. And that's what you get in your TPH CWG. Now, all the examples are for nice clean materials. You know, this is just a mixture of 2 oils, and it works great. The problem is where you're getting humics from your soils, because humics sit in this aromatic area over here and these 2 fractions over here on the right. So just to give you some reminder of the acronyms, these are what you might see if it's 2D gas chromatography. You're going to see a 2D in there, and either the aliphatics or the aromatics, depending on which fraction's being labeled. Or for the total, you will see EH, 2D, and total. You'll notice there's no CU in there. There's no cleanup. Okay, it's just everything extracted by the GCGC system. Now, this has been a problem because, or is a problem, and you guys need to be aware of it as well, because when we bring a lab on board with our HWOL data file, and well, over the last 3 years now with these acronyms, we send them a sample of a filter cake, is what I actually send them, that I've worked on over the years. And we ask for everything extracted. We ask for a cleaned up extract. We ask for TPH CWG. We ask for WAC and mineral oil. And one of the reasons for doing that is not to worry about whether a lab gets exactly the same number as another lab, which they're never going to do, but really kind of the relative position of the results between those 4 different TPH tests, for example. Now, so one of those tests we always ask for is TPH CWG. And this slide here gives you a snapshot of how 4 labs currently, as far as I'm aware, do these tests. Okay, so if we go to the first one, Element or Exober Jones or whatever you're used to calling them, they're using what I call the traditional method, which is based on the TPH CWG guidance. They use a hexane acetone extraction. They use a silica gel cleanup, and then they give you the fractions for the aliphatic and the aromatics. So if you look to their acronyms, you'd see everything extracted with a cleanup, plus the headspace analysis. Remember, that's the C5 to C10 bit, through a 1D chromatograph, gas chromatograph, and the number we're interested in is the total of all the aliphatics and the aromatics. Now, ALS, another lab I work with, they went to GCGC a couple of years ago, at least now. They use the same solvent extraction as Element. And what they are doing is, because they're not doing a chemical cleanup, they're doing a mathematical cleanup. Okay, hence for mathematical, you see this HWOL acronym. So on their reports, you will see EH, everything extracted, 2D for GCGC, total, with the #1 after it indicated they've done a mathematical cleanup, and I'll show you which bits they subtract in a minute. Plus the headspace analysis, which is still done traditionally with a 1D gas chromatograph. Okay, so you can see the two tests, the 5 to 10 and the 10 to 44, added together effectively in the acronyms. Envirolab, they were doing, let me go to ChemTest next. So ChemTest have moved to GCGC as well. They're not doing a chemical cleanup unless you specifically request it. Okay, now when I sent my filter cake to them, I got the results back. The results from TPH CWG were larger than any of the other results. And when I questioned them, they said, oh, well, TPH CWG, if you want to clean it, you go ask for it. And then I say, well, hold on a minute, the TPH CWG standard includes a cleanup. So why isn't it there? And there was no clear answer to that. So if you want to clean up from some of the labs, you're going to have to realize that they're doing it differently. So look at the acronyms, look to see whether there's a CU in there or not, because apparently they will do a chemical cleanup. Now, Envirolab were similar in that they weren't doing any type of correction for humics, but I've been pleased to see they've taken my ideas on board, I guess, and now they're also doing a mathematical cleanup, and I'll show you how a mathematical cleanup works in a minute. So the key thing is, for those of you relying on TPH CWG, you need to understand what your lab has done. Are they doing either a chemical cleanup or a mathematical cleanup, or is it everything extracted from your soil? So how do they do a mathematical cleanup? Well, this is the output from the GCGC system that ALS use. Now, I apologize for these graphs, and the labs do as well, because they're not in control of these graphs. They are created by the equipment manufacturer, who at this point doesn't seem to understand that customers would like decent graphs out of them that you can read the labels. So if I go through the labels, this says solvent, so this is a solvent peak going through, so ignore that one. Then here we've got the aliphatics, so this is C21 to 35 down here, and I can't even read them myself, but this is going up to 44. This larger section up here are all the aromatics. So once again, here's C21 to C35 aromatics. Now you'll notice on here there are these 3 polygons. So this is where ALS has, I think they spent about a year appraising the system and trying to work out where the humics sit. These are any peaks in these 3 areas. These 2 here are fatty acids. These are humics. They will subtract from the total. So they will give you a smaller number. Now for me, this isn't a soil, this is some of my data here, this is from a filter cake. And this big peak here, this bright yellow one, is actually cholesterol. So for my non-soil waste stream, this still wouldn't have been good enough for me, but at least once you understand what's going on, then you can work with it. So their acronym is EH2D total #1, because they subtract these 3 areas. Okay. So other labs who have moved to GCGC, and as I said, it's quite a lot of them now, you need to work out, you need to ask or know whether or not they're doing a cleanup, or whether you have to ask for it, which to me is disingenuous if you think you're getting TPH CWG. This is one I got recently from Envirolab, and you can see it's a different machine, actually a much better plot. So here you can see the aliphatics down here. This is the solvent down here, so ignore that one. And then we have the aromatics up here, and you can clearly see the bands. This is where they estimate the humic sit. So anything within this polygon, they will subtract. I have asked them to consider also the C16, C18 type fatty acids, which would sit over here somewhere, to consider removing those as well. But anyway, this is a big step forward. So once again, these guys are doing a mathematical cleanup. Now, if you want to read a little bit more about it, you can go to haswasteonline.com, go to the info button and publications, and you can download a kind of white paper I wrote 2 years ago now, which just goes through the basics of TPH analysis. Okay, so it doesn't give as many examples as in this talk, but at least if you want to learn a bit more, then the paper hopefully is fairly straightforward to read and will fill in some of the gaps from the presentation today. So going back to the original question, is TPH always TPH? I mentioned that we're referring to petroleum hydrocarbons, but what I want you to consider, are we getting oils from combustion of petroleum, coal, plant and animal derived? How can we tell? We can start looking at site history. We can look at double ratio plots. We can look at other techniques, including something called TICs, tentatively identified compounds. So I realize I'm running a bit late, so I better scoot through some of these. This is a double ratio plot where you take 4 PAHs, put them on a plot and compare them with petroleum products, combustion products, coal derived and plant derived. And to this, we and others have added some of these ellipses. This is from pyrolysis, incineration of municipal waste, lots of plastics, and you can see that they all plot in here. If you're doing coal tars, they will all tend to plot. This is coal tars from roads, for example, not pure coal tar, then refined coal tar to use as a binder in roads. They tend to plot in the top of this coal, bottom of the coal tar ellipses. So we've added this extra ellipse up here to help see them. Now, I should add that I rarely see anything plot in the petroleum products. Now, with a caveat is that I don't work on fuel spills, for example. But normally when I'm dealing with contaminated land, helping some of you guys with your work, I rarely, if ever, see anything plotting in here. It's generally over here in the ashes, the coals, the coal tars. Tentatively identified compounds, or TICs, when you ask for your SVOC suite, you're only actually getting a predefined list analyzed. So it varies from lab to lab, no doubt, but they might have a list of 250 organic compounds, and all they're doing is using mass spectrometry to look for those individual compounds and measuring whether they're there or not and giving you a concentration. All right, anything else that might be there, they're not going to pick up. So that's a defined list. Whereas your TPH test, whether it's EPH or TPH CWG, is giving you a concentration for all the hydrocarbons in that range. Okay, so here's an example. This is a chromatogram showing some peaks. Okay, let's get backwards, sorry. And you can see these peaks here, and this might be, I don't know, several thousand milligrams of TPH, but you don't know what that is. If you ask for TICs, okay, they will actually analyze those peaks, and you find out these are fatty acids. This big one here is cholesterol. Okay, so you understand much more about your waste. This is everything extracted, by the way, from a waste. This is a filter cake. Now, the other thing to be aware of is when you guys ask for an interpretation of your TPH, you can get different interpretations depending on whether you're looking at everything extracted or whether you've gone through a cleanup. So here's our EPH in my language, 20,000 milligrams. You've got these peaks, okay? And this is the lab's interpretation, fatty acids and naturally occurring compounds. Okay, so that's everything extracted. When you go through a cleanup and you effectively remove these peaks, because they all contain oxygens and things like that, to look at just petroleum hydrocarbons, you can see, let me just go back a slide. You can see this scale here is up in the 1,000 mark. This scale here is sub 10. No, might be different machines, but the The idea is okay. This interpretation was degraded diesel, lube oil, and possibly naturally occurring compounds. Now, the lube oil is a debate for another day, but here you can see the diesel. Here you can see these double peaks that I mentioned earlier on. Now, this diesel should not have been in this waste. It was a filter cake from processing hoof and horn meal from India. But India had had some typhoons. The whole factory had got flooded. They used diesel as a fuel, and it had got into the feedstock. So that's where the diesel came from and had to be cleaned up. But the point I'm making is that you get a different interpretation depending on whether you've got everything extracted or whether you've gone through a cleanup. Okay, because everything extracted, if I go back a slide, might be dominated by some big molecules or big concentrations of something. Do a cleanup and you start to see, I mean, this was coming through 1,000 milligrams plus, so it was right on the border of hazardous and non-hazardous. Another example, this is wood dust from a waste wood incinerator. They came to me, and you can see here, this is how labs should be presenting the acronyms in your report, so you can see, without trying to poke through an appendix, see what you're dealing with. So, so this lab is using headspace analysis, but normal gas chromatography rather than mass spectrometry. And you can see down here, you can see they're doing a cleanup. Okay, so this is TPH CWG, 1D gas chromatography. I think this is I2 analytical or someone. And you can see here we've got all of this aliphatics, 2,400, but not much less on the aromatic side. They didn't have the chromatogram, or they did have one chromatogram, which was this one. And I said, well, TPH CWG should be 2 chromatograms. So where's the missing one? So when they went back to the lab then apologized and said, effectively, they've given the customer this chromatogram, okay, which wasn't for TPH CWG, it was for everything extracted. And this chromatogram is not, let's call it a normal chromatogram from the flame ionization detector. It's from a mass spectrometer. And you'll see this word here, TIC, at the top that they left on there. That stands for total ion count. So there's a whole different technology. It looks like a conventional chromatogram, but it's not. But the fundamental thing is why did they even give it to the customer? Why didn't they give them the correct chromatograms? And believe it or not, they said it's because most customers don't understand them, which is a fair point, and they just want a pretty picture for their reports. These are the correct chromatograms. So C20 is about here. Okay, this is the aliphatics. These are mainly waxes, and then these are the aromatics. So one thing to be aware of, yes, I do always say get the chromatograms, start learning from them, start understanding them a bit more, but do be careful. Some labs are just not giving you a picture rather than real data. Going back to the TICs, these are the tentatively identified compounds. And remember, we used it a couple of slides ago to look at cholesterol and stuff. When we applied it to this effectively sawdust from this cleaning up waste wood for incineration, it gave us a whole bunch of compounds. You see the CAS registry numbers here, see the names. If you then do a search and a bit of research, you find out that many of these, guess what, it's waste wood. These are pine resins and things like this. You think you walk through a pine wood, what do you smell? You're smelling aromatics. Okay, they're not the aromatics you worry about with your contaminated land, your naphthalenes and your pyrenes. These are other aromatics that aren't considered harmful. Also found flame retardants, and then you also find some overlap with petroleum hydrocarbons in terms of simple alkanes, these saturated hydrocarbons. This is up in the waxes. And of course, fatty acids. So none of these are related to refining of crude oil. They're naturally occurring materials, plus things like flame retardants. So putting it all together, this is a filter cake I analyzed some years ago. We had existing work done by another where they had EPH. This was everything extracted. And had waxy acids, waxes and fatty acids. No diesel or gasoline, that was important. The ticks identified these fatty acids. They also found caffeine, ibuprofen, cholesterol. This is for glass recycling, so you can imagine bottles of HP sauce and stuff like that. This is the EPH. This is everything extracted. Okay, and you can see these big peaks here, which were identified by the tick analysis. So here your fatty acids. And then this is about C20 here. You can see the waxes coming in. If you do a cleanup, those big peaks disappear, and all you're left with are the waxes. Okay, so you understand a lot more about your material that you're dealing with. Notice the difference in the scales, 600 down to 60 effectively. So this has, just to sum up in the last couple of slides, one of the reasons that hopefully this is of interest to you all is that if you have inflated TPH concentrations, you're more likely to find your waste hazardous. Disposal of hazardous waste is much more expensive for non-hazardous. You've got increased gate fees, landfill tax, etc. If you're just dealing with WAC and you're trying to put your material into the inert category of landfill, and your mineral oil is more than 500, and that's because it hasn't had a cleanup system, well, then you're going to fail inert WAC. That's going to cost you more. Now, if you're doing human health risk assessments, you're going to have these raised concentrations from the C17 to C35 range. Now, I'm not an expert on this stuff. I don't do human health risk assessment, but I would have thought that could have an impact on you. So you guys can tell me about that one. So what you need to understand then, finishing off, is you need to understand TPH a lot more. You need to understand the basics of hydrocarbons, names of them, families of them, understand the basics of gas chromatography, 1D and 2D. You need to really understand what type of TPH test your lab has actually done. So make sure when you go back to your lab later on today or tomorrow, you register with them that you want to see the acronyms on all your reports. Some labs only do it if they think you're a waste customer, i.e. you get the HWOL data file. Well, I put it to you all that you would need it whether you're doing phase 1, phase 2, not phase 1, phase 2, whether you're doing WAC or anything else. So please go back to your labs, put a little bit of pressure on and say, look, we want to have the acronyms, we want to understand what we're dealing with. I also recommend you ask for chromatograms and start trying to then understand those a bit more. If your lab, when you get your acronyms back, is giving you GCGC for your TPH-CWG, then you need to determine whether or not they're doing a mathematical cleanup or a chemical cleanup. And if you're going to try and investigate more about your oil, your TPH, your petroleum, your hydrocarbons, I should just say, then you might want to consider more than one type of TPH test to investigate what's going on, including ticks. Okay, I'm sorry I've used up a whole hour, so I apologize if some of you have to disappear, but yeah, I guess we now go to questions.
Thank you very much, Ian. That was absolutely brilliant. We've not had that many questions in. I don't know if you've stunned everybody into silence or not. We do have a question from Robert, however. He says, from a human health risk point of view, not accounting for the humics, etc., will be a conservative approach, and so accounting for these will help ensure unnecessary remediation and greater sustainability. So as a regulator, where they don't always have control over what they actually get coming across their desks, could they get away with only considering this when there's an issue?
Yes, you could. My main point to all of you is that when you regulate local authorities, many consultants, we get our data third hand. And so if the original purchaser of the testing hasn't insisted on the acronyms being in the report, then you can't go back and get them because you don't have that contract with the original lab. So if they're in the reports all the time, then you can then make a more informed decision as to whether or not the presence of humics might impact your human health risk assessment.
Yeah, and I guess Robert had already identified the fact that one of the main advantages of it is that you are making sure that you're not doing unnecessary remediation, because you're you know, I mean, I think that has definitely got to be taken into consideration, you know.
Yeah, it costs money.
Yeah. Got some more coming in. One from Simon that says, would FOC analysis also help to enable humic compounds to be blank corrected from the TPH?
What did you say, FOC?
FOC, yeah.
I don't know what FOC is.
Fraction of organic carbon.
Fraction of organic, so that's like total organic carbon, I guess.
Yeah, sort of, yeah.
If your lab is measuring, let's call it total organic carbon, I certainly understand what that is, then those are measuring hydrocarbons across not just 10 to 40 or something, but way up into the hundreds of carbons. So your total organic carbon, even if it's into fractions, I can't think what an FOC data set might look like, but you've got to remember there are many other hydrocarbons above C40 that we don't have to worry about. I think he needs to explain what FOC are before I can answer that better.
I think Simon, you're sort of like comparing apples and pears, and it would really be appropriate to use something like fraction of organic carbon, just because of the way that the analysis actually works. Labs do it in different ways, but it might be that fraction of organic carbons actually came from like a sort of like a ignition test or something like that, you know, where like it wouldn't really be appropriate, I don't think.
No.
A different Simon has a question saying, my screen is really small here. What evidence do you have for the relative efficiencies of different chemical cleanup procedures for removing interferences without also removing some of the target compounds, for example, different solvents, column packing, residence times, etc.?
We don't have access to any of that information. I mean, you can always dig deeper and deeper and deeper. We're just trying to understand the fundamental differences between the tests. All the labs use different systems, and even if you just go back to, well, why aren't we all using the same solvents, or why aren't we finding out the optimum solvent for a particular matrix of soil? It's not happening. And then part of that is because the labs are trying to do everything as quickly and efficiently as possible to keep the prices down. So you get what you pay for.
I mean, you certainly would be able to go to individual labs and get that data, but then you would have to be comparing it between labs as well, because as you say, they all use different methods. Yeah. And I guess and one of the biggest things is the actual extraction, the front end extraction, and what they're actually using.
That's another
as
kind
a solvent.
I'm
yeah.
Sure.
Because at the end of the day, what goes down the GC is only what you've actually managed to get out of the sample in the first place.
Yeah.
And then you can go way back to actually what you've actually sampled. Let's not go there. So bearing in mind we're just about over 2 o'clock, we'll just leave it there. Thank you very much, Ian. That was absolutely brilliant. Just a reminder, everybody, again, to go and check out the website for our conference, and also by all means have a look at the Ian's website or the Has Waste Online as well. So hope you all have a great rest of your day, and thank you very much for joining us. Thank you.
Thanks, everybody.